let me get myself feeling real good. You know how I'm going to do that. See, it always works. It's time for Organic Chemistry with your host, me, Dr. White. Now, I was looking at the schedule, and I also know test number 2 is usually the hardest test of the semester, tea break. Oh, lifesaver. And because of that, I'm going to postpone test number 2 by 1 week. It was supposed to be, if I look at the syllabus, let me find out if I'm lying to you or not. I'm not. Can everybody see the syllabus? Thank you. All right. You notice today is the week of the 12th of October. There's only 19 more shopping days till Halloween, but I suspect this Halloween, I know I will not be opening my door for any trick-or-treaters. Hope they're smart enough not to go around. But if you look at this, test number 2 was this Wednesday. Well, I think you guys could use more practice, so I'm going to move it to next Wednesday. I'll put out an email to that effect. And I think that will help you with having some more time to do practice problems later this week, this weekend, Friday, Saturday, and Sunday. I did a really good impression of being a vegetable growing in my lazy boy chair and sort of. But I will this week get out an email and an announcement about test number 2, how many points. It will cover alcohols, thiols, and I'll put this in the email and the announcement, epoxides, ethers, ketones, aldehydes. Wow, that's a lot of stuff. But you'll be able to do it. Do the practice problems. Today, hold on a second. What? I don't know how that got there, but anyways, it's gone. Today I'm going to go through the ketones and aldehydes practice problem. You're welcome, JC. All right, now, quick thing, historically, I've done this, and I'll put this in the email. Test number 2 usually has about 35 points nomenclature. Remember, nomenclature, there are 2 types of problems. One is, here's the structure, give the IUPAC name. The other is, here's the name, IUPAC, or common name, draw the structure. And then there'll be reactions, give the organic product or products. But since you've all lost your rookie status, I will have 3, yes, 3 synthesis problems, give the starting materials. But as you notice throughout the chapters we covered, there are a couple of reactions that I will not give synthesis problems. Example, hemiacetal formation, ketal and acetal formation, and hydrolysis of acetal, ketal, hemiacetal, ketal, and the Grignard. I think I mentioned a few others throughout. I won't give synthesis epoxide reactions of ethylene oxide. I won't give synthesis. See what a nice guy I am? So, like I said, I will be postponing test number 2 by 1 week. Instead of this Wednesday, it'll be a week from Wednesday. Any questions? Remember, in my class, there's no such thing as a dumb question. I'll have my office hours tonight, so stop by if you have any questions. All right, let's get going. Let's talk about the aldehyde ketone problem set, because I finished that up last week. Can everybody see that on your screen? Aldehydes, thank you. All right, I should warn you, there are a few mistakes I haven't had a chance to correct in here. I'll try and point them out. All right, let's go through it one page at a time. And if we look at this, the question is, give the IUPAC name for the following. And what do? You look for what's different. Ooh, carbon-oxygen double bond with a hydrogen and carbons. That's an aldehyde. How do you name it? Find the longest chain with the carbonyl carbon. Remember, the carbonyl carbon is carbon double bond to oxygen. And there's 1, 2, 3, 4. Name it as an alkane, butane, drop the E and add Al. Carbonyl carbon is always number 1, so you don't put a number there. Now, if we look at this, ooh, look, oxygen double bond to carbon, carbon's here, carbon's there. It's a ketone. And here you find the longest chain with the carbonyl carbon, carbon double bond to oxygen, and that's 4, butane, drop the E, add ONE. Now, if it's acyclic, not in a ring, you need a number, and that always has the lowest number possible. So that would be 2, 2-butanone. And let's do C. Oh, look, we have an oxygen double bond to carbon in a ring. How many carbons? 1, 2, 3, 4, 5, 6. Cyclohexane. Drop the E, add ONE, cyclohexanone. Now, in a ring, carbonyl carbon, carbon double bond to oxygen is always number 1 because it rocks. It's the best. Remember Dr. White? Oh, I forgot. No, I never told you this. Time out for something very, very, very personal. If somebody asks me what kind of chemist you are, and I'm being totally honest in my heart, yep, right side, correct side, I would say I'm a carbonyl synthetic organic chemist, because most of the things I've done have been with the amazing carbonyl group. So I told you I'd tell you personal things about me this semester, and that's extremely personal. Now, if we look at D, we have what's different? Carbonyl. Bond to hydrogen, carbons, aldehyde. How many carbons in the longest chain? 7. Heptane. Drop the E, add Al. Remember, alcohols have an OL ending, so on your test a week from this Wednesday, don't forget, be clear if it's Al or OL, because you don't want me guessing, because I can guess wrong 50% of the time. You don't want that to happen. So drop the E, add Al, because it's an aldehyde, and then the carbonyl carbon is 1. These carbons are spoken for. Oh, look, it's your favorite old friend, the methyl group. There are 2 of them. Dimethyl, carbonyl carbon is 1. The methyl groups are on carbon 3 and 5, 3,5-dimethylheptanyl. If we look here, what do we have that's different? Oxygen, double bond to carbon, carbons here, carbons here. It's a ketone. What's the longest chain? 9. Let's find out if I didn't make a mistake. 5, 6, 7, 8. So it is 9. No name. Drop the E. Add ONE. It's a ketone. What carbon is the carbonyl carbon on? Carbon 3. Remember, that always gets the lowest number because it's most important. So it's 3 known and known. Oh, look, an isopropyl group on carbon 6. Now, let's do the next one. I'll tell you something personal about me again. Ooh, I'm really letting out all the secrets today. Must be the medication I'm on. Anyways, draw the condensed structure for the following organic molecule names. How do you do that? You start at the right and move left. Al ending, aldehyde, carbonyl with an R group and a hydrogen, carbonyl, carbon, double bond to oxygen. If this were an E, hexane, 1, 2, 3, 4, 5, 6. Carbonyl carbon is always number 1, and there's a hydrogen there. Remember, there's 4 bonds to carbon. Now, you could have put the carbonyl on this side and have it go this way. Dr. White learned, and I've never changed the habit of always putting my carbonyls starting on the right. And good habits I don't change. You want to start on the other side, you could have. All you're doing is flipping the molecule. Let me remind all of you, molecules are not glued to paper. They're like your hand or other things that can move around in 3 dimensions. So if I said, quick, close your eyes, and you did, I went like that. Oh, look, different. No, you just rotated it. So molecules do the same way. In the answer key, I'll always put the carbonyl on the right. And if you put it on the left starting, that's okay, because I have a piece of paper signed by the Board of Regents of Michigan State University saying I know how to do that, my PhD diploma. All right, let's look at B. If we start here, O-N-E ending. Oh, it's a ketone. If this were an E octane, 8 carbons. Where is the carbonyl? Carbon 3. I started this way, 1, 2, 3. You could have started at this end, 1, 2, 3. Either one would be correct. It's the way I do it. Like I said, I'm biased. I don't change things that have been working all my life. All right. Let's look at C and D. These are the only 2 common names in aldehydes and ketones I asked you to learn. And C is acetone. Acetone, nobody calls 2-propanone. It's the simplest ketone, 3 carbons. The carbonyl is on the center one. You can draw it either of these ways. For those like using a stick, which I do, you can draw it that way also. The other common name I asked you to learn is formaldehyde. Nobody ever calls this methanal, which would be the correct IUPAC name. It's the simplest aldehyde where R is H, and you can draw it either of these 2 ways. Now, if we look at E, we have 2 tert-butyl cyclopentanones start at the right. Oh, and the ending ketone, if this were an E, cyclopentane, 5-member ring. You can put your carbonyl on any carbon, but I put it on top like you would. Oh, look, it's my favorite group, the tert-butyl group on carbon 2. All right, here's one of the mistakes. Oh, I feel so bad. Dr. White's too lazy to change this, so I didn't. But this group right here on F should be N-propyl, CH2, CH2, CH3, not isopropyl. I got it right in G. All right, any questions on nomenclature? Going once, twice. All right, let's move on to reactions. Now, the reactions give the organic product or products. If we take this molecule, what is it? A primary alcohol, oxidize it, lose a hydrogen here, hydrogen from the oxide, form a carbon-oxygen double bond, and you get an aldehyde. In this case, R was methyl. If we look over here, and don't forget on this carbon, the hydroxy group, there's a hydrogen. So this is a secondary alcohol. Oxidize it, that's what the O in the brackets means. Lose hydrogen there, form a carbon-oxygen double bond, and you get a ketone. In this case, that's to the carbon of the ring. Now here, Dr. White did the chemistry in C. Favorite contrast test, put a big, scary molecule. And now, what's different? Remember, all these reactions, when you're doing a reaction, or even nomenclature, look for what's different. What's not a carbon-carbon single bond, or carbon or hydrogen should get your attention like that. And for these chapters, it's oxygen. Keep your eye out for that. Now here we have hydroxy group on carbon. It's a secondary alcohol, same as above here. Between, you lose the hydrogen here, hydrogen there, and form a carbon-oxygen double bond. You wanted to put the oxygen on top, that's fine. These are oxidations. Let's go to this one. We have a benzene ring. Ooh, what's different? Carbonyl with a chlorine and carbons. This is an acid chloride. Unfortunately, it's the only time this semester I can talk about these. And here we're reacting with aluminum chloride, trichloride, and this is Friedel-Crafts acylation. You put a carbonyl with an R group on the benzene ring. It doesn't matter which carbon you put it on the benzene ring, because we're always going to start with benzene, even though you can use other aromatics. I'm not getting into it because we're not talking about directors, other than the lab you did. Oh, by the way, don't forget to hand in the lab. That's due Wednesday. And therefore, what's our methyl? I have my benzene ring, carbonyl, then my R group, methyl. This is one of those special reactions where you made a carbon-carbon single bond. Ooh, this is a good one. Let's see if I can. No, I can't. Here I have a benzene ring. Ooh, another benzene, but it's attached to a carbonyl, carbon double bond oxygen, with a chlorine, aluminum trichloride, is Friedel-Crafts acylation. You lose the chlorine, and this carbonyl with the R group is bonded to the benzene ring. This case, hold on. Two more rings, my answering machine will get it. Sorry about the interruption. I wasn't sure who it was, so I didn't want to hang up on them. All right. Now here, R is a benzene ring, and you make this new ketone. Notice both R and R prime are benzene ring. This is an aromatic ketone, and ketones like this are used as sunscreens in your suntan lotion. All right, let's continue on. Next couple of equations, next couple of reactions, go back and practice. Why? Because students get these wrong on test number 2. And I don't want you to get it wrong on test number 2. Now here, what's different? Carbonyl, hydrogen, methyl group. It's an aldehyde, but it could have been a ketone also. Getting ahead of myself. What's different here? Carbon, carbon, hydroxy group on a carbon, alcohol. And notice here, H plus is acid catalyst you're going to do this in the lab, you could use something like sulfuric acid. And what do you get? You get a hemiacetal or hemiketal. Keep your eye on the carbonyl carbon. That's where the fun is. And what's attached to it, our prime or our double prime, especially also if our prime is H, still attached to it. This opens up to the alcohol, and the oxygen, the R group from the alcohol, is attached to that same carbon. Whatever carbon is attached to the hydrox group in the alcohol is attached here to the R group in OR. So if I look at this, R prime is hydrogen, R double prime methyl, R is ethyl. Here's my carbon, that was my carbonyl, H and methyl, OH, O, CH2, CH3. And the next page, A is the same, except we're doing a ketone. Now, let's look at B. Ooh, something different. Wait, what's different here? Carbon, double bond oxygen, ketone. It's in a ring. R prime and R double prime are connected together. Next, ooh, two of something. Carbon, carbon, hydrox group on alcohol. We have two alcohols and we have acid catalyst. What happens? Keep your eye on the carbonyl carbon. What's attached to it is still attached to it, R prime or H and R double prime. And then you lose this. It comes off as water, but I don't put down inorganic stuff. And the carbon that was the carbonyl group, you have two OR groups on. And here's one, here's the other. And here's my R prime, the ring. Here's my carbon, that's this one right here. What's attached to it? O and O. And the R group is isopropyl. And the same thing here, except, let me tell you, here's a benzene ring. It won't react with an alcohol under these conditions. Therefore, this is R prime, double prime. This is R prime H. This is my two alcohols. And here's what you get. Now, let's take a look at D. If we look at D, the question is, what's different? I have a carbon with a hydrogen and carbons, but here's the giveaway. You have a carbon with two oxygen bonded to it. There's stuff on the oxygen, but when you see that, there's only two types of functional groups, acetal, ketal in this case, or if one of the oxygens has a hydrogen, hemiacetal, hemiketal. In this case, the acetal or ketal, this is an acetal, and I'll never ask that on the test, undergoes the same reaction. The carbon with the two oxygens, this carbon, what's attached to it directly, R prime and R double prime, still does, becomes the carbonyl. The OR group becomes an alcohol. If you want to put a 2 there, you can. I wouldn't. And therefore, if you come back here, R prime hydrogen, R double prime ethyl, R methyl. So what's attached to this carbon with two oxygen directly is still there. That becomes a carbonyl. Then here, my R groups are methyl. This one is a little tougher. Again, look for what's different. Oxygen, oxygen on this carbon. This is one of only two places you'll see that. Actually, this reaction, acid, water, hydrolysis. By the way, I'll teach you later in the semester, this is the exact same type of reaction that your body uses to break down carbohydrates. And now this carbon has the ring and isopropyl attached to it. It still is. And that carbon, if we look up here, become a carbonyl, carbon double bond to oxygen, and the R groups on the oxygen become the R of the alcohol. Listen carefully. Notice the oxygen is on the N carbon of 3 carbons. Therefore, it's on the N carbon of this 3 carbons. All right, let's go to 5A. And here, hydrogenic catalyst. Remember, carbon double bond to oxygen has a pi bond and a sigma bond. And you know how to break pi bonds. You learned that in carbon-carbon double bonds. Same thing happens here. What's attached to the carbonyl carbon stays attached. You break the pi bond, and each atom of the double bond gets a hydrogen. So if I look here, ketone. Here's my carbonyl. I break the pi bond. What's attached to it? Our prime and our double prime still attached to it. I have my alcohol at H, OH. Could have drawn it this way. You could have also put the hydroxy group on top and the hydrogen below. Now if we look at C, same reaction. This is now a ketone. I'll break the pi bond. Each atom of the double bond gets a hydrogen. Remember, we don't show hydrogens on a ring. Now, this is different. LiAlH4. This is lithium aluminum hydride. And this does the same thing as hydrogenic catalyst, but this will only work with carbonyl, ketone and aldehydes. This will not touch a double bond. I won't throw one of those on a test, but that's the importance, which I did mention. So here, what do we have that's different? A ketone. Lithium aluminum hydride, second step acid and water. What's attached to the carbonyl is still attached. And you break the pi bond, and each atom of the double bond gets a double bond, a carbon-oxygen double bond gets a hydrogen. Our double prime is still attached to that carbon, and you break it, and you have OH and H. Could have written it this way, or you could have put the hydroxy group on top, hydrogen below. And next one is the same thing. And here, same thing, ketone, lithium aluminum hydride, second step acid and water. The 2 atoms of the carbon oxygen double bond, you break the pi bond, each one gets a hydrogen. You don't show hydrogens on a ring. All right, one of the things that I left off the problem set, which I shouldn't, is the following. And that's how you make a Grignard reagent. Remember, if you write a Grignard reagent like this, it's wrong because nothing like that exists, so don't. And since I didn't give you any practice problems, I'm going to give you a couple now. Remember, the carbon with the halogen is the carbon the Grignard reagent MgX is bonded to. And it's your turn. I'm going to take a break while you do it. What would be the product or products that are following? And when you're done, give me a thumbs up like one of you've already done, or smile. I think everybody's done. Again, how do you do these problems? And it's also true in all of organic chemistry. I always do it. Look at a molecule and look what's different. It's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention. Oh, look, a halogen, magnesium. Here's the reaction. This is my R group. You break carbon-carbon single bonds? No. I'll form the Grignard. What's X? Iodine. And remember, there are 4 bonds to carbon. And the Grignard reagent and the reaction were discovered by Victor, or invented by Victor Grignard, my hero in organic chemistry, who won the Nobel Prize for that. Oh, let's do another one. Let's do a synthesis. What would I react with magnesium to make the following molecule? Everybody done? Nope, not yet. All right, let's see, everybody's done. Yep, you're all done. Let's do this. Look at the molecule, what's different? Oh, look, magnesium chloride on a carbon. This is a Grignard. How do we make Grignard? X is equal to chlorine, bromine, or iodine. One of the halogens, never fluorine. And what's my R group? This. So over here, what do you start with? Which carbon has the Grignard on it? This one. Therefore, the halogen, and notice I have chlorine here, will be there. And that's how you make a Grignard. And Dr. White used these in my PhD research for my thesis. And then I also use the next reaction. And that is, let's look at 6A. And what's different? Carbon, double bond to oxygen. Ooh, we have up here, carbon, magnesium halide, acid, water. Grignard. What's attached to the carbonyl stays attached. This attacks, see, Dr. White and all organic chemists are violent, watch out. But anyways, this attacks is how we say a bonds, we use the word attacks, the carbonyl carbon opens it up to an alcohol, and then you make something very special, very rare, very, very important, a carbon-carbon single bond. There are very few reactions that allow you to do that. And what's our prime and our double prime, ethyl and methyl? You can switch these, doesn't matter. That's still attached to that carbon. It opens up to an alcohol. And what's our triple prime methyl? This reaction I'll never give as a synthesis. The making a Grignard I will, this one no. That's cruel, unusual punishment. And as it stands now, it's still outlawed by the Supreme Court. At least today it is. And if we look at B and C, same thing. We look at B, what do we have that's different? Carbon, double bond to oxygen, hydrogen, methyl group. Here's my carbon-carbon. So this is an aldehyde, carbon-carbon, magnesium. Oh, Grignard, second step acid and water. Our prime is hydrogen, our double prime methyl. What's attached to the carbonyl carbon is still attached to that carbon. Here I have this carbonyl becomes an alcohol, and I make that special thing, a carbon-carbon single bond. What's our triple prime? Ethyl, so here it is. In C, remember, the carbon with the Grignard is the carbon bonded to the carbonyl carbon that forms this alcohol. If you put it on the N carbon, I will mark it wrong, because it is. And finally, let's talk about this reaction. And my gift to you, don't tell anybody I'm being nice, please. Ruin my image. I have two of the same aldehyde, carbonyl, hydrogen, R group. Base, and I've forgotten the problem set to put down water, and NaOH is base. You can use other bases, but for this class, I'll stick to sodium hydroxide. And remember, the alpha carbon of an aldehyde is true for a ketone, but I'll keep it simple for aldehydes, has acidic protons, the base removes it, one less hydrogen, and then this carbon, which becomes a enolate anion. Don't forget, Dr. White is world authority on enolate anions. That's what I did in my PhD thesis and my last US patent. I used them too. And this attacks the carbonyl carbon, opens it up to an alcohol. This again is one of the special reactions when you make a carbon-carbon single bond. And here, this attacks that. So I rewrite that. Lose one hydrogen. Remember, there are 4 bonds to carbon. Common mistake, which I take off points, is that a student puts CH2 with a bond, and you got 5 bonds to carbon. No, that won't happen. And here, you form the bond to here. What's attached is still there, opens up to an alcohol. Here, enolate anion will not attack a benzene ring, but it sure will attack a carbonyl. And finally, here's the last mistake. I have my 2 aldehydes, 1, 2, 3, 4, 5, 6 across. And notice I have 1, 2, 3, 4, 5, 6 across there. But this bottom one, I have 1, 2, 3, 4, 5, 6, 7. There's an extra CH2 there. And that's how you do it. And why don't you try this one for your fun and enjoyment on this? Hopefully we get some more rain Monday afternoon. In case you forgot, I'll help you out. But you should learn these. Write them down 5 times. Everybody done? Okay. Good news. The wooziness in my head is starting to clear. First time that medication did that to me. But I was warned, don't drive while you're on it, which I don't have to. All right, let's look at this reaction. What's different? Ooh, carbon, double bond to oxygen, carbonyl. Got carbons here and here. It's a ketone. It could have been an aldehyde, but it's not. This is our prime. This is our double prime. What do I have here? Carbon, carbon, carbon. Ooh, magnesium bromide. This is a Grignard. Second step, acid and water. This is my R triple prime. And remember, keep your eye on the carbonyl carbon. What's attached to it, our prime and our double prime, are still there. The carbonyl opens up to a hydroxyl group, and you make something very special, very rare, very important, a carbon-carbon single bond. So it's attached to my carbonyl group, our prime and our double prime, methyl. And then I get my alcohol on this carbon. No, you don't have to put a dot inside. I'm just showing you that. If we were in a classroom, I'd be using my index finger to show you, keep your eye on that carbon. And I'd probably still even put a dot in there with a marker. And what's my R group? 3 carbons. Which carbon has the Grignard MgX, the end one? And notice you made a very complex tertiary alcohol. And I don't know how to make that simply, except to use a Grignard, and then it's a very easy, simple reaction. As a synthetic organic chemist, carbonyl synthetic organic chemist, who's also an industrial chemist, I know acetone, this is right here, is cheap. I can make this very cheaply, this Grignard, and this I can make now directly. And why don't you try this one? And since you might not have memorized all the reactions yet, I'll help you out. And there you go. A little help from Dr. White. All right, looks like everybody's done. Look for what's different. Carbonyl, hydrogen carbons, aldehyde. Oh, look, the same aldehyde. Psst, that's the giveaway. Aldol condensation. Shh, don't tell anybody, gave it away already. And you're reacting with base and water. What happens? You form the enolate anion, remove a hydrogen there. So my alpha carbon, the one attached to the carbonyl, I'll remove a hydrogen there, and this enolate anion will attack the carbonyl carbon. What's attached to this ketone, aldehyde carbonyl carbon, is still attached to it, but the alpha carbon, I'll lose one hydrogen, and then this bonds to the other aldehyde, becomes an alcohol, which is why this is called an aldol condensation. And notice there's 3 carbons there still attached. Remember, you don't break carbon-carbon single bonds. And notice this carbon right here has 4 bonds, and I don't have to do anything more, and I'm done. It's time for a break. I'm still alive. I'm still working good. I'll see you in about 5 minutes. I can go downstairs and sit on my couch and rest my back. Even though this chair I have, this office chair, is quite good. But before I do that, any questions? With that, I'll see you in 5. Back. Let's get started. I could take another 30 seconds. Go back to sleep. Nope. All right. Any questions on aldehydes or ketones? Ooh, I forgot to do something. Any of you, when you pass by a gas station, think about that gasoline contains ethanol, that's an alcohol? Or if you happen to be in a place that sold liquor, if you happen to see a bottle of vodka, like Grey Goose, Absolute, you know, the good stuff that Dr. White likes, and think about that contains ethanol, that's an alcohol. Did you happen to pick up a bottle of rubbing alcohol? That contains isopropyl alcohol, also known as 2-propanol, and that's an alcohol. Did you think about that? I'll try one more. Anybody use any nail polish remover? So I didn't have time to polish my nails. I don't. But anyways, actually my grandfather, back when I was a little kid, it was most men, if you were paid, it was, a lot of men did, they'd have a clear coat always put on their nails after they had it manicured at the barber shop. But anyways, use acetone to take off your nail polish and think that acetone is a ketone, and that is in nail polish remover. Remember, when you're not in my class, think about organic chemistry. It's all around you, and it won't hurt. All right, any more questions or any question? Well, guess what? It's new functional group time. I got to fire myself up, and that always does. And this new functional group I'll be talking about are carboxylic acids and their derivatives. And the new functional group is carboxylic acids and their derivatives. Derivatives, what's that? That's something derived from. So I'm going to talk about this new functional group, carboxylic acids. Then I will also talk about other functional groups that are made from carboxylic acids. And this chapter, I'm going to talk about something that's really sour. I'm also going to talk about stuff that smells good. And then you won't believe what I'm going to get into this chapter. He's talking about that. Yes, I can even talk about that. Remember, I'm going to talk about things that I'm not taking a moral stance on anything, good or bad. It's stuff you can buy using organic chemistry. So let's talk about this new functional group, carboxylic acid. And let me just close a few things. All right, you all should see on your screen carboxylic acid. You see it? Thank you. All right. This won't be on a test, but carboxylic acid, new functional group, yay. And it contains a carbonyl, carbon double bond oxygen. By the way, I forgot to mention, you should know how to say with words and how to write what is a carbonyl group. Really, you should know it. I hope my eyes pop open wide. And since I didn't do it, I better do it right here. It's so important. You should know this for test 2. Carbonyl group. Carbon double bond to oxygen. Carbon or carbon atom, either one works for me. Again, this is for test number 2. Coming up a week from this Wednesday, I'm postponing it. I'll put out an email today or tomorrow. And you should know carbonyl group, which is not a functional group, but is in many functional groups. How do you draw it? Carbon double bond to oxygen with 2 lines here, or you can put R prime, whatever. But anyways, carbon double bond to oxygen. How do you say that? What in words, or write in words? What is a carbonyl group? Carbon atom, double bond to oxygen atom, or you could have just put down carbon double bond to oxygen. Know this. All right, let's get back to carboxylic acids. I just wanted to cover that because it's so important. Everybody see the carboxylic acid? Thank you. And the reason why I reminded, because a carboxylic acid also has a carbonyl group, but now also it has a hydroxyl group on the same carbon, and we call that a carboxylic acid. How they got that name, I have no idea. And the general formula, now I have it here. My software likes to take out the carbon here and put a Ben. The way you can write it is like this, where I'm not showing true bond angle, or you can write it like this. And notice you have carbonyl group and the same carbon hydroxyl group. And this is a carboxylic acid. Now, if you look on the internet, and I'll do this later on, there's other ways of drawing carboxylic acids. And this would be one, which I rarely use, but I do use this. So you could, instead of having this and this separate, notice 2 oxygens, and one of them has a hydrogen. That's what this says. And that's how you, and any one of those is perfectly correct on a test. Now, as I mentioned, next number of chapters, I'm going to introduce you to a new functional group. Meet my friend, the carboxylic acid. And yes, it is. I worked at one company where I was the laboratory manager, in charge of both research and development in North America, and also at the plant that was on site where our research center was. I was the quality control manager too, which is why I had the title laboratory manager. And we made carboxylic acids to the tune of about 2 million pounds a week. How many of you have ever seen the container or the vehicle that delivers gasoline to gas stations? That's called a tank wagon. And tank wagons hold 50,000 pounds. Divide 50,000 to 2 million, that's a lot of tank wagons. We also use railroad cars, which are different size, but can hold up to 4 or 5 tank wagons. We ship a lot. And when we get into fats and oils, I'll talk more about what I do at that company. Now, The question is, how do you name, I'll be introducing you to carboxylic acid, say hello to carboxylic acid, carbonyl with a hydrox group and an R group on it, carboxylic acid. Next, I'll go through the IUPAC names, common names, where you find it in your daily life. Then we'll get into the fun part. How do you make them? And the even more fun part, how do you react them to make things? So, how do you name a carboxylic acid? Under the IUPAC nomenclature rules. Find the longest carbon chain, which includes the carbonyl carbon of the carboxylic acid. Name it as a alkane. Now, at the end of the alkane, drop the E at the end of the ANE of the alkane and replace it with the letters OIC and the word acid. Again, find the longest chain that has the carbonyl carbon, name it as an alkane, drop the E at the end of the ANE, replace it with the letters OIC, acid. Just like an aldehyde, carbonyl carbon of a carboxylic acid is always number one, and we never put a number there for where it is, like you did with a ketone, a cycloketone. Next, name and number all other substituents like methyl ethyl, as you always did. Now, this number 5 I'll never put on a test, because frankly, I've never used it either. I know it. When the carboxylic acid is attached to a ring, now, its ending is carboxylic acid is added to the cycloalkane name. Usually common names are used, not this. All right. Let's learn how to name carboxylic acids. Now, what would be the IUPAC name? And give the IUPAC name for the following 3 points each. Nomenclature is important. What do? You look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen. Get your oxygen here and here. And notice they're to the same carbon. And you have an R group. And this is a carboxylic acid. How do you name that? Find the longest chain with the carbonyl carbon. In this case, 1, 2, 3, 4. Name it as an alkane, butane. Drop the E, add OIC, and the word acid. Oh, I should tell you, not to ruin your day, but I will. Butanoic acid, remember, the carbonyl carbon is always number one, and everybody knows that, so no number. I take off points if you put a 1 there. Now, butanoic acid, one lab somebody managed to break a bottle of butanoic acid. And butanoic acid, not to ruin your lunch, but I will now, smells like somebody just threw up. It's disgusting. And I helped clean it up, and afterward I went home, threw out the clothes I was wearing, and this changed. Because once you get that odor on you, you don't want to put that in your washing machine. Luckily, when I was working in that lab, I would wear older clothes. That was not a pleasant memory, but that's part of organic chemistry. Let me do another one. If we look at this molecule, same question. What's the IUPAC name, excuse me, for the following? And you look for what's different. If we look right over here, oh, look, what's not carbon, what's not hydrogen, what's not a carbon or hydrogen or a carbon-carbon single bond, oxygen here, to the same one. It's got carbons attached to this carbon. This is a carboxylic acid. How do you name it? Find the longest chain with the carbonyl carbon. All right, 1, 2, 3, 4, 5. That's one chain. Then 1, 2, 3, 4, 5, 6, 7. So I hope you all agree 7 is greater than 5. What's 7? Heptane. It's a carboxylic acid, so you drop the E and add OIC and the word acid. Am I done? No. As soon as I say heptanoic acid, that's all spoke. Oh, look, there's something left over. Remember, the carbonyl carbon is always number 1. So on carbon 3, what do we have? 3 carbons to the center carbon, isopropyl. And what carbon is it on? Carbon 3. So this would be 3 isopropyl heptanoic acid. I better share the fun. Why don't you try this one? What would be the IUPAC name for the following molecule? Look for what's different. So one person's done. I'll wait till everybody else is. If you're done, give me a thumbs up. All right, I think everybody's done. I'll give you another 30 seconds. All right, let's do it. Now, what do we have here? What's different? Ooh, 2 oxygens to the same carbon. One is double bonded. The other is a hydroxyl group. I've got carbons to that. This is a carboxylic acid. And here, how many carbons in the longest chain with the carbonyl carbon? And we have 1, 2, 3. And you know that's, I hope you do, propane, what you did for test. Now it's a carboxylic acid, drop the E, add OIC, and the word acid. And now, am I done? Yes, because the carbonyl carbon, which is 1, you never put a number in front. So that's propanoic acid. Oh, let's do another one. These are fun. And the question is, what's the IUPAC name for the following? See, two people done. If we were in a classroom, I'd be reminding you, when you're done, look up and smile. I'd see all those smiling faces. No, not always. It's optional. All right, anybody need more time? All right, let's do this. Look for what's different. What's not hydrogen, what's not carbon. And if we look here, oxygen, oxygen's the same carbon. One's carbonyl, carbon double bond, and the hydroxyl group have carbons. And what is this? This is a carboxylic acid. How do you name them? You find the longest chain with the carbonyl carbon. Let's do 1, 2, 3, 4. That's one chain. 1, 2, 3, 4, 5, 6. That's another. And finally 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think you all agree 9 is greater than 4 or 6. So what do we call an alkane? 9 carbons. And I better give myself some more about that. Stop. Thank you. So 9 carbons. Hold on one second. Nine carbons is no name. It's a carboxylic acid, so I'll drop the E, add OIC in the word acid. And then, as soon as I say that, this is all spoken for. Oh, look what I have here and here. I have a methyl group and an ethyl. Remember, the carbonyl carbon is 1. And the methyl is on 3, the ethyl is on 4. Now, there are two possible answers here. I'm not holding you to the IUPAC alphabet rule, but this would be 4 ethyl, 3 methyl, NaOH acid. Say that 5 times quickly. And if you put the 3-methyl first and the 4-ethyl second, I would give you full credit. If you forget the hyphen there, I don't take off points for that. And that's how you do carboxylic acids. Everybody see the common names on the screen? Thank you. All right, carboxylic acids have been around for eons. Organic chemists or before organic chemists, alchemists before chemistry knew about them. Now, there are a couple common names I would like you to know. The first one is formic acid. And formic acid, remember carboxylic acid, has this structure. And it turns out R can be H. So formic acid has this structure. Now, the IUPAC name would be methanoic acid. Nobody ever calls it that. We call it formic acid. And remember, for common names on a test, I can give you the common name and ask you to draw the structure. I'll never ask you, here's the common name, here's the structure, give me the common name. Why? Because you can see these on labels. And one of the nice things about ingredients on labels, my class, when you're done this semester, you'll be able to pick up things and say, oh, I know what that structure is. I've already shown you, but I'll go over it again before the semester's out, how you can also look up the material safety data sheet that will tell you how dangerous something is. Now, let me tell you a little about formic acid, because we're getting into the really good stuff now. How many of you have ever heard of the fire ants? Those are ants that their defensive weapon, they spray a liquid at who's ever attacking them. And they're called fire ants because if you get it on you, it feels like it's burning. You're burning or you have a heat burn. Fire ants. Luckily, they're still down in Texas and Southwest. Hope they never come to Illinois. But anyways, why are they the fire ants? Well, like I said, it feels like you burn. Now, when you get certain acids on your skin, we call that an acid burn. Luckily, I've never had it, but in the lab at the other school, I actually had a student who got some because he didn't follow directions on his arm. And it looked almost 30 seconds later like if you slapped hot metal on your skin. It was a bad burn. Even though I treated it immediately after he did that, it still was very nasty. Well, the fire ants, what they spray is a heated solution of water and formic acid. So the formic acid, which gets on your skin or whatever animal is attacking them, gives them a burning sensation like they're on fire. And that's how they got the name fire ant. All right, let's go some more. Now, the next one you should know is acetic acid. And acetic acid is when R is a methyl group. Nobody ever calls this ethanoic acid. It's always acetic acid. Now, I'll give you a chance to write it down. All right. Guess what? You have acetic acid in your house. No, I don't have it in my house. Yes, you do. If you go in the kitchen, you'll find it. What? Well, let's take a look. If you take approximately 4% acetic acid and mix it with approximately 96% water, what do you get? Vinegar. Vinegar is just a very dilute solution, a small amount, 4% acetic acid in water. So next time you're with friends, neighbors, or loved ones, and you're in your kitchen or you're in their kitchen, you can hold up their bottle of vinegar and say, you know, that's got acetic acid, a carboxylic acid in there. No, don't. You lose a friend quick. Get someone upset. But think about it. Organic chemistry, like I said, is all around you. And vinegar is an example. Oh, by the way, all vinegars have acetic acid in them and water. The only difference is other small components that give it a different taste. Example, plain white vinegar, not named after me, but that's what it's called, has this mainly pure acetic acid water. Now, there are different types of vinegars like wine vinegar, champagne vinegar, or rice wine vinegar. I like rice wine vinegar. That's their best brand is Marucan. Get the gold, not the green label. Oh, did I tell you, if you're all good organic chemists I've ever met in my life are also good cooks. If an organic chemist tells you he's a good organic chemist and a lousy cook, he's lying to you one way or the other. But anyways, next time you're in the supermarket, now they actually sell them in most, look at the rice wine vinegar and the Marucan Japanese rice wine vinegar, the gold, not the green label, is good stuff. And also certain champagne and wine vinegars are good too. Now, balsamic vinegar has acetic acid, but it has a lot of other chemicals in there to give it the taste. If you look at balsamic vinegar, it's dark, almost like my shirt, and that's because there are other chemicals in there that are made when they make that. Now, the last one I'd like to talk about is benzoic acid. Now, benzoic acid is when R is a benzene ring. This is benzoic acid. And turns out that's both the IUPAC and the common name for this molecule, this carboxylic acid. And IUPAC, in their infinite wisdom, said, just like with benzene and toluene and phenol, we're not going to get those organic chemists to change. They've been calling this benzoic acid too many eons, and they kept it. And this turns out to be an important molecule, and I'll teach you where this chapter where it's used. So you should know common names: formic acid, when R is H; acetic acid, when R is methyl, and you should also know you can find acetic acid in vinegar. And that's really what vinegar is acetic acid and water. And then you should know benzoic acid has this structure. And since it's both the common name and the IUPAC, on a test, I could ask, which I usually don't do with common names, but this is the IUPAC name. What's the name, IUPAC name of this molecule? And the answer is benzoic acid. Have you noticed it has the OIC ending and acid? Now, why they didn't call that benzoic acid? Well, probably somebody eons ago just called it benzoic and it caught on. All right. Next two slides, click, I'm turning the switch. We'll be on test to the off position, but still good stuff to learn about. Now, it turns out you can have long chain carboxylic acids, another way of writing it. Hold on. Switches off, where you have a long chain, an alkyl chain, just carbons and hydrogen. Here, remember, CH2 in a bracket like this means it's repeating, and then can be a number of numbers, and you have the carbonyl. Now, if you count all these carbons, when it's 12, we call that lauric acid. When it's 16, palmitic acid. These are common names. I'll teach you later some of them when we get into fats and oils. When it's 18, stearic acid, 18 with a double bond. oleic acid. And these are, what I'll teach you later, come from fats and vegetable oils. And we use them in our daily life, and you do, because they're used to make things in your cosmetic and personal care items. Bet you didn't know your cosmetics and your personal care items like shampoo, soap, laundry detergent are all organic molecules made to keep you happy and clean. All right, switch is still off. Let's look at some hydroxy acids, and those are carboxylic acids that also have an alcohol. Now, one of the interesting ones is this molecule. Remember, it switches off on this slide, lactic acid. Notice it's a carboxylic acid. I drew it this way. I could have also drawn it this way. You don't need to know this structure, but I thought it'd be interesting to go over it, and I'll explain why. This is lactic acid. How many of you ever worked out real hard with weights or running long distance? I'm a weight person, not a runner. And after a while, you feel that burning sensation in your muscles. That's due to lactic acid. How Mother Nature created that your body breaks down something and tells your muscles, hey, you should slow down or stop, unless you're watching the movie Running Man by Arnold Schwarzenegger, where he says, no pain, no gain, which is not really true. But that molecule, when it gets in your body, in your muscles, causes that burning sensation. Again, lactic acid has a hydroxyl group. And by the way, this is a carbonyl. So this is called the alpha carbon, just like in ketones, the aldehydes. And this is lactic acid. Now, what I'm about to tell you is this something interesting. No way am I taking a moral view on anything or stand. Now, lactic acid, well, first of all, if you go to big box store like Target or Walmart, you'll find a company called KY that sells interesting personal lubricants, which is used for personal stuff. And one of the habits, or not habits, I wouldn't call it really a hobby, but a mental pursuit Dr. White has is, I see a product and say, how do they do that? And a number of years ago, KY came out with a personal lubricant they call the warming gel. And you put it on a certain personal part of you for a certain activity, and it made it feel warm. I wonder, how do they do that? And I picked up a box at, I think I was at a Walmart, and looked at the ingredients. Near the end, I saw lactic acid. And what that product was doing had a small amount, and that warming sensation was due to an acid burn from the lactic acid. Not enough to harm you, but to give that warning. Now, years later, they took it out because I think they had some issues, people getting slight burns from it, who knows. And they replaced it with another molecule that when the moisture on your skin, when you put that on there was a heat given off by, it's called hydration of a molecule, which I'm not getting into, by forming hydrogen bonds, and that's an exothermic reaction, gives off heat. Now, one thing I sort of know how to do, but I'm not 100% how they do it, is they also have a product called fire and ice that both heats and cools. I'm pretty sure I know how to do the fire part. The ice, I think I do, but so when you go anywhere, you see products, how do they do that? A lot of the times it's with organic chemistry. Now, let's look at another one. Remember, switch is off, and that's citric acid. And I could have drawn it, my software was giving me problems the day I drew it, so I drew it this way. Sometimes my software doesn't like to do it the way I want to do it, and it fights me, and I finally give up. If we look at this molecule, this is citric acid. Now, if we look at there, look at, ooh, 1, 2, 3 carboxylic acids, plus an alcohol. And this is called citric acid. And most of you have tasted citric acid. Again, you don't have to know the structure. Where do you taste it? Well, citric acid has a very, very, very sour taste. Have any of you ever bitten into lemon? Ooh, is that sour? Or had real sour lemonade? What's giving it that taste? Citric acid. Also, how many of you have ever used limes? I like limes better than lemons myself. And if you bite into that, ooh, that's pretty sour. Or if you use it, I like making not lemonade, limeade. It's much nicer. You know, sugar brews from a lime and some water, and I really like that. Tastes better than doing the same thing with a lemon. And that has the same citric acid. It only has less of it. Now, citric acid, years ago, organic chemists found how to make it in a chemical plant or in a lab, and then a chemical plant, so you don't have to squeeze limes or lemons. And it's a white solid. How many of you are familiar in the last maybe 8, 10 years, there was this trend, which I don't like, but it's selling good, in children's candy to make it super sour. For some reason, they've convinced kids the more sour it is, the better it is. Not me, I'm a sweet candy person. Give me Hershey's bars or M&Ms or stuff like that. Kit Kat bar, ooh, Halloween's coming up. But anyways, how do they make it super sour? They just put in more citric acid. The more citric acid in there, which they get from a chemical plant, it's food grade. In other words, chemicals you can put in food makes it more sour. If I had my own company and I had the credit rating to buy it, in a week or two, I could get 100,000 pounds of citric acid. Now, interesting story. One place, you can buy it many places, pure citric acid, it's white solid. I bought some, and when I got home, I wondered, wow, I wonder how sour it is. So it went like this. Mistake, it was really sour. More sour than if you bit into a lemon. Switch is still off on this slide. Everybody see the physical properties of acids, carboxylic, thank you. All right, now, some of the ones, like I told you, butyric acid, have sharp or unpleasant odors. They have a sour taste for lower. MW means molecular weight. They're polar, again, switches off. They have high boiling points or melting points because they can form hydrogen bonding, and the lower ones are soluble in water. And I think you all agree, lower molecular weight carboxylic acids have a sour taste to them, or really sharp. How many of you have ever done shots of vinegar? I'll bet 0. But vinegar and other carboxylic acids are used in many cuisines to get that sweet and sour taste. Example would be Swedish sweet and sour meatballs, Asian sweet and sour pork, and, oh, I'm getting hungry. I'm gonna see it now. But those are used in cooking for that thing. Now, carboxylic acids are acids. And why? Because they dissociate in water to yield a carboxylate anion and a hydronium anion. Click, switches on. What I'm talking about, carboxylic acids, will be on test three, not 2. So, but still, you should know this. Let's talk about the acidity of carboxylic acids. Now, in organic or chemistry, this is a general way of writing an acid. Let me change colors. This is a base. You can have a proton transfer, and the base will neutralize an acid to make a salt. Now, if you just have water, which you can have proton transfer, the acidic proton, which you should know, is the hydrogen on the oxygen of a carboxylic acid. So in water, it can give up its proton to here and form this, and this is called the carboxylate anion, which you should know. And the carboxylic acid, like I said, donates a proton. That's the definition of a Bunsen-Lowry acid, something that donates a proton. So what does that mean? Well, before that, switches off for the slide. What makes a carboxylic acid acidic? Now, if I take ethanol and acetic acid, ethanol it's a tiny arrow in an equilibrium, which means it really doesn't go to the right. Forms the alkoxide anion plus H plus if it's dissociated. Now, we have acetic acid, and this is true for any carboxylic acid. It's much more acidic, meaning why I have a larger arrow. Now forms the carboxylate anion, and it gives up H plus because it's an acid. Now, what makes this more likely to happen, meaning a stronger acid? And again, switches off, but I thought you liked. That's the effect of resonance stabilization of the carboxylate anion. Just like you learned in a benzene ring and an enolate anion. If I can draw more than one resonance form, this goes here, this goes here. I'm showing just for the electrons, and I'm not flipping this over. This is actually different. The more resonance forms you can draw, the more stable it is. So this is less stable than this because you can draw resonance forms. And that's why carboxylic acids are acids. If you're reading the book, anybody buy the book? Skip section 10.5. If I look at this, I think it's time, let's take a break instead of me rushing through this. I'll see you at 2:50, about 6-minute break. I'm going to go sit down on my couch in my living room, which is, even though it's a comfortable chair, that's real comfortable. And I'll see you in a couple minutes because I'm going to gung-ho and do the whole day. Because if you notice, see the medicinal effect of talking about organic chemistry has had on Dr. White? A good one. I'll see you in about 5.5 minutes. I'm back. Bet you thought I wasn't coming back. I did. All right, let's get back to what we were talking about, carboxylic acids. And because the carboxylic acid is an acid, and if you react it with a base, you'll get a salt, the first reaction switches on, and my software doesn't like putting carbons in. I'll rewrite it. If you take a carboxylic acid, react it with base, sodium hydroxide, or sometimes I'll do sodium hydroxide and water. What happens? This is an acid, this is a base. You make a salt. The carboxylate anion is a salt. Plus water. On my test, that looks better. I asked for the organic product or products. You don't have to put this down. Now, let me rewrite this a better way. You can take a carboxylic acid and react with a base, and I'll write the base like this, where M for my class is equal to sodium, potassium, or lithium. And same thing happens. You have an acid-base reaction. The only difference is what's the cation. I'm not going to write down water because you don't have to. And this you should know. So let's take a look at this reaction. And I'll do some and then let you have some fun. Now, if we look at the following reaction, the question is give the organic product or products for the following. Don't forget, these reactions are how organic chemists make molecules that you use in your everyday life. And if we look at this, we have what's different. Ooh, hydrox group to the same carbon with a double bond to oxygen, carbons here, carboxylic acid. What do we have here? A base, which I'll write this way, and water. Again, sometimes I'll forget to put the water down. Remember, for my class, M is sodium, potassium, or lithium. This is an acid-base reaction, and you get the carboxylate anion plus water, but I'm only asking for the organic product, so you don't have to put down water. And remember, this is called the carboxylate anion. So what's our ethyl? Another way of thinking of it, whatever attached to carbonyl carbon stays attached. And now, 2 carbons. I have my carboxylate anion. What's M? Sodium. And that's what you get. Now, if you notice, I always put my anions like that. If you want to drop the charges, I won't take points off. Years ago, I had a student who I took off a point because he didn't show the charges. He got upset with me. We debated it, and he proved his point. And I said, you're right. You don't have to put the charges there. The way he proved his point is You said, how do you write table salt? Like this or like this? Which it really is, Na plus Cl minus. I said, you're right. So you don't have to, but I always will. And this is a straight acid-base reaction. And it's your turn. Try this. What would be the organic product or product for the following reaction? And everybody, I forgot to look at my video link. Everybody done? Thank you. And if we look at here, what's different? Carbon, double bond to oxygen with a hydroxyl group on it. Carbon's here, carboxylic acid. What do I have here? Ooh, a base, lithium hydroxide, which I'll abbreviate like this, where M can be lithium, sodium, doesn't matter what, or potassium. What do you get? Acid-base reaction, and you get the carboxylate anion of the carboxylic acid. In this case, what's M? Lithium. What's my R group? Isopropyl. What's ever attached to the carbonyl carbon stays attached. Another way of thinking about it, you start with 4. In this reaction, you better end with 4 carbons. And that's the carboxylate anion you get. Oh, this is fun. Let's do another one. Now, this molecule has 2 functional groups, and one of them is a benzene ring, and benzene rings do not react with sodium hydroxide and water. And with that, have some fun. All right, looks like everybody's done. What do we have here? Oh, look, benzene ring, but that won't react. What's this? Carbon, double bond to oxygen, carbonyl with a hydroxyl group. This is a carboxylic acid. And it turns out this is my R group. What am I reacting with? Sodium hydroxide is a base in water, which I'll abbreviate this way. And now, give myself a little more room here. This is an acid-base reaction. Remember, M can be sodium, potassium, or lithium, the alkali metals, and I'll teach you also, you can have other bases too. And you get this carboxylate anion. What's M? Sodium. What's our benzene ring? And you make this molecule. Now, one of the things I've been doing more and more in this class is asking you always to ask the question, why am I learning this thing? And the obvious one is you want to get a good grade so you can get into school or program. Well, why learn this chemistry? Well, let's look at what you just did. Now, later this chapter, I'll teach you the IUPAC names for these compounds, but this is called sodium benzoate. And it has a structure, and you learned how you can make it from benzoic acid with sodium hydroxide and water. So what? Well, if you're from the Chicagoland area, like I am, I've lived here all my life, except when I was in Michigan for grad school. And off and on, I'd spend weeks at a time in Europe, but most of the time I've been here. And if you ever buy the stuff in a can or a plastic bottle that's got bubbles, carbonated, non-alcoholic, we call that pop. On the East Coast, they call it soda. Now it's pop. Dr. White's favorite is Dr. Pepper and Werner's. If you've never had Werner's, you should. It's a very spicy ginger ale that's very highly carbonated. Oh, you can get it at Jewel. I don't know where else you can get it. I never look anywhere. But if you look on the label near the end, you'll see sodium benzoate. And what is sodium benzoate? It's a preservative. Helps keep it fresh. I don't know what that means. Either kills stuff in there or whatever. But they put that into pop, other pops too. And you'll see that as a preservative. And now you know how to make it. So these reactions I've been teaching you are used to use things, you don't realize it, but are in your everyday life. If you're a pop drinker, I've cut down way down because I used to drink a lot of Werner's and Dr. Pepper. I still have, if you go in my pantry, you'll see 3 cases of Dr. Pepper, the 12 packs, and 3 Werner's. One of each is open about halfway. Always have an emergency supply. Yeah, you might get snowed in. You don't want to run out of Dr. Pepper. Oh, let's do one more. What do you react with this to make this compound? And remember on test 3, and also be on test 2, which I'm postponing a week, you can, there will be 3 synthesis problems. All right, looks like everybody's done. They're giving me that look. You're giving me that look like, get to work. So I will. All right. Look for what's different. What's not carbon, what's not high. Carbonyl with an oxygen minus and a cation. and carbons. This is a carboxylate anion. We're reacting with what? Oh, base, potassium hydroxide, which I'll abbreviate like this. Remember, M can be sodium. Ooh. Potassium or lithium. In this case, it's potassium. And what do I start with? A carboxylic acid. What's my R group? T-butyl group. I have my carbonyl right here, which is this, and it's a carboxylic acid. And that's how you do that. Now, there's a special reaction. Wrong one. Right one. Uh-oh. Hold on a second. Let me sign out of something. There we go. What happened was I forgot to close this one, the Adobe Cloud that's on this machine. It messes up sometimes. All right, let me just check since I've been playing around. Everybody see the reaction of a carboxylic acid with sodium bicarbonate on your screen? Can you see it? Thank you. All right, now, this one I'd like you to know, this is also a base. Sodium bicarbonate, you know, is baking powder. That's the stuff in the little yellow or red can, unless you get a generic like Myers or other supermarket chains. And let's look at this reaction with a little detail. Now, what I'm going to show you, you just need to know the overall reaction. And did it again. Hold on, I'm going to close this and reopen it. Hang in there. All right, sometimes, because I've got so many things running on this computer, it goes, I'm confused, and it was. All right, we got that cleared out. Let's take a look at this. This is a carboxylic acid. This is baking powder, sodium bicarbonate. You should know when you react a carboxylic acid with sodium bicarbonate, you get three things. This is going to be a rare question where I'm going to ask you give all the products of the following reaction, not just organic. Let's look at what's called the mechanism. What I'm going to write now will never be on a test, but you should know the overall reaction, which we'll practice. Now, this is sodium bicarbonate. Its actual structure is this. And when you add sodium bicarbonate to a carboxylic acid, this gets transferred over here. And what you get is the carboxylate anion of the carboxylic acid plus this molecule. You don't have to know the name of it, but Dr. White does. It's called carbonic acid. And notice I have brackets around it, which means it can't be isolated. Because if you look at this molecule, if I look here, oh, I've got an H here, an OH, two hydrogens of oxygen, two hydrogens of water. And left behind are a carbon and two oxygens. And this immediately breaks down to make water and carbon dioxide. The little arrow here tells you it's given off as a gas. So whenever you take baking powder, sodium bicarbonate, react it with carboxylic acid, you get three products, the carboxylate anion, water, and CO2. Everybody see the whiteboard? Thank you. So let's take a look at and this is different than I normally ask, because normally I ask give the organic products, but now give all the products for the following reaction. Well, what do we have here? Carboxylic acid. What are we reacting it with? Sodium bicarbonate, otherwise known as baking powder. And what do you get? Acid-base reaction. You get the carboxylate anion, but you also get water and CO2, carbon dioxide bubbles, given off as a gas. So if we look up here, what's our ethyl? What's attached to the carbonyl is still attached. It becomes the carboxylate anion. But you're asked give all. So you also get water plus CO2, carbon dioxide. And I like to put the arrow there. It's given off as a gas. And it's a fun reaction to do. I'll let you try one. And it's your turn. What would be the organic product or products for the following reaction? No, I said it wrong. Bad, Dr. White. Give all the products for the following reaction. So used to saying it the other way, it just comes right out of my brain and mouth. All right, looks like everybody's done. Look at what you're reacting. What's this? What's different? Carbon double bond to oxygen, carbonyl with a hydroxy group and carbons, carboxylic acid, got it written up there, sodium bicarbonate, baking powder. And what do you get? A carboxylate anion and water and CO2. So what's my R group? These four carbons, or think whatever attached to the carbonyl is still attached. And this is a carboxylate anion. Remember, this is sodium. Remember, there are 4 bonds to carbon. And I asked, give all the products, and you get water plus carbon dioxide given off as a gas. Oh, let's do one more. Remember, give all the product or products. All right, I think everybody's done. Let's take a look at this. What's different here? Carbonyl, hydroxyl group, carbons, carboxylic acid. Ooh, baking powder. And what do you get? Acid-base reaction, you get the carboxylate anion of the carboxylic acid you started with, plus water, plus carbon dioxide. What's our methyl? So I get this molecule, this carboxylate anion, it has a common name, sodium acetate, plus water, plus CO2 given off as a gas. Now, remember at the beginning of the semester, I said you learn a lot about me? Well, now is one of those times. I'm bringing back a really fond memory. And that is when I was like in first grade, my father, who was a pharmacist and loved chemistry, I become a chemist, I don't know. But anyways, all my friends thought he was the coolest dad around. He was, showed us something. And back then, the big thing that was going on when I was in first grade and later on was the space race between the Americans and the Soviets, the communists, otherwise known as the Russian Empire, Russia and its satellite areas. And it was in everywhere, including toys and candy. Now, when I was like that in first grade, they sold this candy that was in a little rocket ship, plastic tube and fins. Oh, warning, Dr. White's going to do some artwork, so be careful. Don't laugh too hard. But anyways, and this material, or the candy, was the most awful candy in the world. How do you know that? Because when you got your little rocket ship, and there were these little beads, you'd take it, a 6-year-old taking candy, take the cap off, go to the garbage can, dump it. Now you had a little rocket ship. Well, here's what my father taught me, and I showed my friends. They thought he was cool. And that is the following. All right, here's what the rocket ship looked like with the candy in it. Again, you can laugh at my, had a cap, an empty tube. It had some fins. It was about 2 inches high. And inside here were the little pellets of candy that was awful beyond awful. You dumped it. And what my father showed me was you take this tube, turn it upside down after you got rid of the candy, and it was like a little test tube. And you put in some vinegar, and some baking powder, and you slam the cap back on it, you invert it, hold it by the fin, and what happens is this reaction, because this is acetic acid, and that's really vinegar. It makes this and this, but it makes this gas, and the pressure builds up. So when you have this like this, again, Dr. White will never go to art school. You have all this, you have that gas, this cap goes flying off, just like you just shut off a rocket. And if your timing was good, mine got pretty good, you could mix it and slam the cap on. And it would go about 5 or 6 feet. And if you're a 6-year-old, that's cool. Now, I do have a sad story to tell you about this. My best friend back then, I haven't seen him in decades. I hope he's still alive. Dickie Gale, he did something bad. He used up all his mother's baking powder doing the rocket ship. And she went to cook something where she needed baking powder, and she found out it's empty. Oh, did he catch it? So never ever use up all your mother's baking powder with the rocket ship unless you tell her it's out. And that's one thing. Now, another thing I should tell you about my father was he loved to cook. And when I was younger, he owned a pharmacy. It was owned, this is before they had chains, which kicked out all the small neighborhood pharmacies. And he'd work Monday through Saturday. And on Sunday, he closed the pharmacy, it wasn't open, and that was his day off. Now I have 2 sisters, one's 7 years older, one's 7 years younger. Yep, I'm in the middle, literally. And some Sundays, he would say, a couple days before this Sunday, it's men only cooking in the kitchen. All ladies have to leave. And he and I would have quality time together cooking. And my mother was a very good cook. He was a better cook. Anyways, we also had a large deep chest freezer. From my parents' generation, a lot of my friends, their parents had it too because they had lived through the Depression. And because of that, you always wanted to have a lot of food in your house, and that's the way to do it. And he'd make a big stock pot. And one of the favorite things he liked to make is spaghetti sauce. And you put in all the, I'm not going to go through the whole recipe, but first of all, how many of you have ever made your own spaghetti sauce and it just doesn't taste the same way as the really high-end Italian restaurants? I don't know how he found out, but one of the tricks is put a little pinch of cinnamon. Now, this was like a 3-gallon stock pot, and he put in maybe less than 1/8 of a teaspoon. Years later, I taught a friend of mine, he made a smaller amount, put in a tablespoon. You couldn't even taste the tomatoes. It was all cinnamon. Now, that's one thing he did. But the other thing, and I don't know how he came up with this, but to make it smoother and much better tasting, he added at near the end some baking powder. Baking powder. Well, let's take a look at the chemistry. Once again, this won't make it into any museum of art. Now, what is in tomatoes and tomato sauce you use to make spaghetti sauce? Citric acid. And remember, citric acid, and I'll just draw it this way, is a carboxylic acid. And if at the end you add sodium bicarbonate, and this won't be on this, well, yes, you should know this. And what happens is you get the carboxylate anion, a salt, plus water, plus carbon dioxide given off as a gas. And if you add an acid and base, what happens to the pH? Remember, pH is how you measure acidity. The pH starts around here, and by adding a base, you increase the pH, make it less acidic, so it tastes milder. And because this also tastes like salt to your tongue, when R is from citric acid in the tomatoes, you cut back a little on the salt normally people put in their spaghetti sauce. And this made it real mild. So by doing this, and also when you do that, you see a foam in there, and a big pot of about a couple gallons, he put in about maybe a teaspoon, teaspoon and a half. Smaller, put in less. Now, a number of years ago, I had a Chem 170 student, and after I told her what you did, and you should try it too, it makes really good spaghetti sauce. And she came up to me a couple weeks after I taught this in class and said, Dr. White, I'd like to thank you. I said, well, you're welcome. What are you thanking me for? Well, your father's recipe for spaghetti sauce. My father and I really love it. I said, well, thank you. I'm glad that. She says, but you don't know why we love it. And I said, you're right, I don't. She says, both my father and I suffer very badly from acid reflux. That's where your stomach acids, for some reason, I'm not a medical doctor, comes up your esophagus and burns the heck out of it. And whenever you eat anything that's acidic, which is tomato sauce or spaghetti sauce, it's quite painful. I worked at one company where another manager had it so bad he had to have an operation to help relieve of the pain he was in a lot of times. So I asked her, well, how did it help you? She said, well, when we put the baking powder in like you taught us, it's less acidic and therefore it doesn't burn. And it was quite nice. Now we can have spaghetti sauce with our spaghetti and not suffer afterward. I thought that was nice of her to share that. So when you go to make spaghetti sauce, don't forget, key secret, add a little pinch of cinnamon, and then at the end, first of all, cut back on the salt a little, add a small amount of baking powder. You mix it in, you'll see like a white foam on top, that's the carbon dioxide, and it disappears, and it tastes really good. And to this day, that's how I do it. By the way, why was he making 3 gallons? Because we put it in quart containers, freeze it, and we could take some out for dinner. Now, I've already mentioned sodium, potassium, sodium benzoate. Why do I have potassium benzoate? Number of years ago, 1 or 2 pop companies came out because the medical science was telling you sodium is bad for your blood pressure. What they really mean are sodium cations, switches off on this slide. And here, in order to make it low sodium pop, they used potassium benzoate, which has the same preservative, and you react benzoic acid with potassium hydroxide. And they were selling a mixture of this. For some reason, it didn't taste as good, and people didn't buy into it, and it's not being sold. Now, how many of you like to go to the supermarket or your local bakery and buy fresh bread? And then the next day, you go use it, it's still good. You don't see any green or mold on it, or a day later. It's still no green or mold going on it. Well, how do they do that? Well, it turns out, I'll show you. Now, if you take a carboxylic acid and react it with calcium hydroxide, which is a +2 OH minus like this, what you'll get, this will not be on the test, all molecules have a net zero charge, you get this carboxylate anion. And that's calcium carboxylate. Now, it turns out, I don't know how they found this out, when R is 2 carbons and it's propanoic acid, one of the rare times you'll see Dr. White balance the chemical equation. This is called calcium propanoate. And this molecule is put into bakery goods like your bread to prevent mold. How that does that, I have no idea. I'm an organic chemist, but I do know how to make it. And so you wonder, why am I learning this stuff? Well, if you like to buy bread and the next day there's no green stuff or black stuff growing on it, that's because of this reaction and this molecule. Now, again, switches off, but I thought I'd teach you some things while you're learning this. How many of you heard that you need calcium for strong bones and teeth too? And so you don't get osteoporosis, which is an unfortunate disease some people get when they're in their older age. Well, do you eat calcium metal? No, calcium is a metal. Just like you're not going to eat iron to get iron in your diet. What are you actually getting? You're getting calcium cations. Now, how do they normally put that into things like, have you ever bought stuff that says fortified with calcium? Well, it's not calcium metal, it's calcium citrate. What they do is react citric acid with calcium hydroxide or other calcium-based products and make calcium citrate and add that. Let's do something real quick. If you look on your screen, everybody see calcium citrate on your screen? Thank you. It's got a little more complex because it's got 3 carboxylic acids. Here's the actual formula right here. 2 of these, 3 of the calcium. And this is the molecule that they put in so your body can get the calcium +2 cations and then give you strong bones and teeth. If I look at the clock, I made it to the end and I feel much better. See the therapeutic effect organic chemistry has on somebody who wasn't feeling well, I'm feeling much better now. But I think this is a good time to stop. And with that, I'll say goodbye. Gang gesund. I better do this. Bye, and I'll see you on Wednesday. And if you have any questions, I'll have office hours tonight too. Bye. See you on Wednesday. Gang gesund.